So let's talk about some pitfalls in working with your process technology. So one is choosing your what process generation you want to use. So you a lot of times might have a desire to use the latest process generation that's out there. Generally, the latest process generation will provide a better power to performance trade-off. But on the other hand, it's also going to be the most expensive, or generally more expensive than an older process technology. So you have to weigh the benefits of the extra performance versus the cost that it's going to cause you. Second, your yield issues on a newer process. Generally, a new process doesn't have as much debug have gone on that process, and so your yield tends to be lower, which means you're going to lose more chips. You're going to manufacture these chips, but less of them are actually going to work. Fewer percentage of them are going to work. Having a fewer percentage of your chips working will actually cost you more time and effort in testing and debugging of your chips. So if you get like 99% of your chips back and they all work, it's pretty easy to test. If 50% of them don't work, it's a much tougher time testing. And also that makes it difficult to know whether your problems, if you have 50% of your chips not working, or let's say you get it back and 100% of your chips aren't working, you don't know whether your problems are due to a mistake in designing the circuit up front versus your circuit is designed perfectly, but the process caused some problem that caused it to not work. And so you're debugging both your circuit and the process at the same time, which increases your cost and your time. Second thing to be aware of is your process. If you go to a new process, it's more than just scaling your old design rules. So you might have had a set of design rules that you were used to on an older process, and you say, oh, well, if something was a 5 lambda distance from one layer to another, I'll still make it in the new process with 5 lambda distance and just use the same design rules, but lambda is just a different value that's smaller. Turns out, no, the complexity of our design rules from one process generation to another is getting more and more complex. You might see 2x the number of design rules. And so there's new design rules that you had never seen before, never heard of before, that you need to design to. It's going to cost you a lot more time and effort doing your layout, and you should make sure to be aware of that and account for that up front when you switch to a new process technology. And third, you need to make sure to account for metal fill early on in your design. It turns out like you might have places where you have long metal wires on critical signals, and you say, I need this to be as fast as possible, so I need to reduce the capacitance on it, so I'm going to space these signals out with extra space between them. As I said before, there's DRC rules that require a minimum amount of density of metal, and so if you're designing that way and you're doing your simulations and everything looks good, and then you don't run your fill flows or your DRC checks for fill and density until later, you might find that you have to insert this extra metal fill. This is going to increase your capacitance, and it's going to change your timing and noise behavior on these critical signals, and you don't want to wait and find out until the very end. You're running these metal DRC checks at late in the design and find out that your circuit's actually broken. So you need to account for this early on. Here's a few additional pitfalls. One is not including some extra calibration structures across your IC die. Typically, people will include things that, so some extra structures that are meant to measure your process parameters, measure like your power supply voltage droop, measure temperature across your die. You might have some special identifiers for showing where the position. I've seen in the past where we'll sometimes have like these multiple metal layers that have like plus signs or various different signs that will show where you are across the die to identify your position. So a lot of times when you're in debug and you're trying to find a given place to put a probe down and measure some value, you need to try and identify where you are on the die, because when you're looking at a really zoomed in, extremely small features, trying to figure out exactly where you are on your IC circuit can sometimes be pretty difficult. And so if you create some special structures in areas across your die that give you an idea of like, oh, okay, I'm in this quadrant because I can see this structure that was created specifically to tell me this position. Those can be useful things to put across your die. And creating probe points. So sometimes you want to probe a given critical circuit, but if you have the only available, if that critical circuit is on a really low metal layer, like a metal 1 layer, and it's a really short metal line, there's no way you're going to be able to probe it. So if you know that you have certain points in your circuit where this is a critical net, you might create an additional, what's called a probe point, where you create an additional pad of metal at possibly a higher metal layer that makes it a lot easier to actually probe that point. Keep that in mind. Fib points on critical signals. Fib is focused ion beam. So this is something where you can actually make connections from one metal layer to another metal layer using a focused ion beam that can basically place additional metal to short two things together. But again, this isn't something that can be done on really tiny circuits that are really local to areas. So typically, if you have some place where you have a critical signal where you think you might want to short it to someplace else or be able to change its behavior somehow, you have to create a specific point to enable you to do that with more success. So things like that are additional structures, but you need to go out of your way to identify places to put them and to put them in, somewhat more manually. Another thing to watch out for is waiving of design rules. So I mentioned earlier that design rules are not necessarily 100%, where if you violate a design rule, you're guaranteed to fail. Sometimes you have some critical structures that are repeated often, like SRAM cells, for example, and you have so many millions of them that potentially that making them even a little bit smaller can give you great savings in area. Sometimes they'll do something like create an SRAM cell that technically it violates certain design rules, but the people who are creating it work with the process team closely enough that they know exactly what violations they're allowed to do and still create a working SRAM cell, just as an example. So potentially waiving design rules can allow you to make something smaller, but you really need to know for sure that it's going to be legal and that it's actually going to be manufacturable and it won't lower your yield. And then finally, one last thing that I'll say is beware of cute logos, and I'll talk more about this on the next slide. So it's actually been quite common in the past to create some sort of, logos on IC chips. And so you can create this out of various different layers of the integrated circuit chip. In the past, as you put a metal layer and then an oxide layer over it and another metal layer, the different layers of oxide would wind up causing different metal layers to actually show up as a different color. And so when you looked at your IC chip, even with the human eye, sometimes you could see like these, nice pretty patterns of different colored wires and stuff. And so people would use that to actually create a colored, colored figures on their die. And a lot of times they do it in a corner or someplace where there wasn't any real circuits. So down below you can see a logo that was put on an image sensor in the past for the Mars rover. So the thing to keep in mind is these cute logos don't always pass your DRC checks because you're obviously creating weird shapes and etc. But a lot of times the designers will say, oh, I'm just going to waive all those DRCs because it's not a circuit. It doesn't really need a function. But the problem is these DRC violations could actually cause some real process problems because you could get, some DRC violations will cause something like as you're going through your processing steps, if you violate a certain type of DRC function, it might cause metal to break off in, if you're in a chemical mechanical processing or step or something like that. A big chunk of metal might break off from one spot and get redeposited into a different spot, and you don't really expect it to be there, and so you wind up stopping your etch at a certain spot, but you really haven't etched everything because you had a chunk of metal deposited in a region where it wasn't supposed to be. And so it could eventually cause real functional problems to other circuits that might be nearby, even though this isn't in an area where you have something that you expect to work. So the other problem that you can run into with logos, and I've actually heard about this happening, is the logo, if you're looking at a particular, like let's say metal layer, one particular metal layer might not look like anything. If you look at the logo after it's fully patterned, you might say, oh, okay, somebody drew a figure there. But the logo might not look like anything with a single metal layer by itself. And so sometimes, like I think I remember hearing somebody had drawn out a picture of a cow that had multiple spots on it, and each of the spots was in a different metal layer, and so they figured once it was fully created, they would have this cow that had multicolored spots all over it. Problem is, the mask shop that was making the photo masks for this looked at a single metal layer, and they saw these blobs of metal, and they said, something's wrong with the mask. We have these blobs of metal over in this corner. And so they threw the mask out and created a new mask. Got the blobs of metal again. They're like, what's going on? And it wasn't until they went back to the design and saw, oh, someone actually put in these blobs of metal when they weren't supposed to. But in the meantime, it costs lots of money because they threw out a couple mask sets thinking that there was a mistake here. So watch out. A lot of places don't allow cute logos anymore. Depending on where you go to work, you might or might not see that as a potential issue. So lastly, I just want to make a comment on historical perspective. Basically, process scaling is still not dead. I say that because I know back in, I think it was around 1999, I wound up listening to a talk by an expert that basically he said process scaling would be dead within 5 years. So back, 24 years ago now, somebody said that process scaling was going to be dead in 5 years. And process scaling is basically a lot more complex than just simply looking at the minimum feature size or gate length of a device. There's a lot of things that are changing and have changed over the years and will continue to change in the future. We're scaling voltage, leakage current, gate oxide thickness, dielectric, and metal materials, the number of metal layers, the type of transistor, using FinFETs, etc., as opposed to planar FETs, and much more is being considered going into the future. The figure below, or table below, shows like all the various different things. This is comparing like Intel versus IBM and various different parameters that have changed over the years, and how that has, all of the different things that have changed. This probably isn't a list of all of them, but just some of the things that have changed over the years. And you can see it's very, very complex. But they're still continuing process scaling, at least minimum for the next 5 years. There's still plans out there on how they'll continue scaling process. And I know they have the next 5 years for sure mapped out, and at least have some vision into 10 years from now, how they're going to get additional scaling. So very interesting stuff, and everyone still predicts that it's going to be dead soon, but hasn't been so far for the last 20 to 40 years. This figure here is just showing how far we've come in the last 40 years or so. Our device sizes and number of devices, or device sizes are decreasing, number of devices per die increasing with each process generation. Back in the early 70s, shown below is initial designs were maybe hundreds of transistors, all drawn by hand and checked completely manually. So both the circuit designs were drawn by hand, as well as the layout drawn by hand. And below you can see people hand drawing layout and basically cutting the patterns out of rubylith. This was a kind of a material that was a red, that's called ruby or whatever, a red material that they would cut out shapes to allow light to go through in the areas that they cut out, and that would be how they create their masks. But nowadays we have billions of transistors per die, and effectively the new compute power that we get from each generation of new microprocessors that comes out effectively allows us to design automation that makes it possible to make the next generation of our designs, because the amount of transistors that are being put on any given die requires enough, the checkers that are required to make sure everything is working requires immense amount of microprocessing power, and so you pretty much need the previous generation of computers in order to design the next generation of computers. So very interesting.